Okay, so we're going to continue on with our history of astronomy. Um, and the next guy that I would put on your T-chart, if you have started one, is Aristarchus. Aristarchus did a few things. He measured the size of the moon. He also estimated the distance to the sun. He was much better at measuring the size of the moon. He was off by a factor of 20. Uh, so he also proposed that the sun was the center of the heavens. So this is the first time that the heliocentric model appears. It's not accepted at this point, but this is the first time that we can go back into literature and find it. The problem at that point is that we should see stellar parallax, which basically means we'll get into it more in a second, but that the stars should look like they're shifting positions as we move around the sun. So if you look at this diagram here, there's a pretty big difference between where the Earth is in January versus July. So what happens is you can get relative distances to these different stars because things that are closer to you will appear to move more. Things that are further away from you will appear to move less. If you've ever been driving along the highway with your parents and you look at the side of the road and the stuff on the side of the road looks like it's flying by, whereas the stuff that's off in the distance looks like it's not even moving. So that's just a quick example of parallax. Moving on to the next era, some more big names that you've probably heard when it comes to the scientific revolution in history. So Copernicus, Brahe, Kepler, Galileo, Newton. Copernicus is a Polish doctor and lawyer. Notice he's not an astronomer. He's just a smart guy who notices stuff. He revisits Aristarchus' now 2,000-year-old idea of the heliocentric model. But he's now able to explain retrograde motion, showing the planets are on different sun center orbits and they pass each other. So as they pass each other, one looks like it goes backwards. But there are still some problems. His model still had perfectly circular orbits, which we now know is not the case, and he still can't see parallax. He publishes his ideas shortly before he dies because he's afraid that he will be persecuted for saying what he's saying because it goes against the church. He is the first person to describe the details of the heliocentric model. So Aristarchus is the first one to propose it. Copernicus is the first one to detail it. So here is the example of how retrograde motion works. If you just line up the numbers 1 with 1 and 2 with 2, this is the pattern that it looks in the sky. So notice as we catch up to Mars in our orbit, Mars starts to look like it's going backwards, and then we pass it, and then eventually it'll start to go forwards. Again, this is kind of like if your dad is in a hurry on the highway and he's flying by people. If you just look out the side of the window, it can look like they're going backwards. Tycho Brahe is basically a rich Danish guy. He uses his money to look at the sky, and he builds kind of like early observatories. They have these pointing and measuring instruments that are kind of like an astrolabe or a sextant that the early mariners, the people on boats, used to use to figure out where they were based on the stars. He builds 4 of these things, and really other than building the observatories, his big contribution to science is the idea that repeatability in scientific measurement is so important, and that more data equals more accurate results. So this is just a picture showing like what his gear tooth system looked like as they were looking up. So Kepler was one of Brahe's assistants, and when Brahe dies, he inherits all of his work, and he keeps doing it and does it bigger and better. So his superior data by volume and precision showed that Mars's orbit is not circular, but it's elliptical. Kepler noticed that the sun was not at the center of the calculated orbit, but off to the side at a focus of an ellipse. Proceeding with this model, Kepler calculated the orbits of the other planets and found excellent agreement with the actual observations. So here's how ellipses work. And if we were in school, we would do this activity. So if you put a piece of string, a loop of string around two tacks and just allow it to guide you around, you'll make an ellipse. This little e value is called eccentricity. If you have an e value of 0, then it's a perfect circle. And you can never get to 1 because that would be a straight line. But you can get to 0.999 repeating on and on and on. So Kepler had 3 laws regarding planetary motion. First, that the planets move in elliptical orbits with the sun at one focus of an ellipse. Second, that the planets do not move with constant speed. They actually move faster when they're closer to the sun. And that the amount of time it takes a planet to orbit the sun exactly once is related to the size of the orbit. Basically, what that means is the closer you are to the sun, the faster you go. We know this. We know that as you get further away from the sun, different planets have longer years. So here's basically the graphical version of those things, if you want to pause that and take a look. This is just the mathematical demonstration of Kepler's third law. So if you actually take this and square it, and this and cube it, they actually equal the same or very nearly the same. Next is Galileo. Galileo does a whole bunch of different things. He is an Italian scientist. He's fascinated by motion. He uses his telescope, which he did not invent, but he kind of perfected it, and he marketed it to the Navy to observe and draw surface features of the moon, observes the changing sunspots, observes 4 large moons of Jupiter, proving that some bodies in the solar system did not orbit the Earth, observe evidence of Saturn's rings, and observe phases of Venus as proof for the heliocentric model. So he did a whole bunch. So we're going to go through some pictures of those. These are the sunspots that you can see. Notice that Mercury down here is looks tiny compared to the sun, and that Mercury could easily fit in one of those sunspots. Actually, the Earth could fit in some of those sunspots as well. These are the phases of Venus. If you notice, when it's closer, it's a crescent. When it's farther away, it's full. So the next picture will kind of explain that. So basically, when we see it as full, it's on the other side of the sun from where we are. So that's why we see it all lit up, but it's smaller. So that this is what accounts for what Venus does. You guys have all seen Venus. It's the first brightest thing that there is in the sky. It looks kind of yellow. Galileo's experiments with motion, falling bodies, coupled with his observations of the 4 large moons of Jupiter, which we call the Galilean moons, raise a question about the nature of planetary motion and what held the planets in orbit. He is condemned for his findings. He spends time on house arrest. He dies in the same year that he dies. Isaac Newton is born. He attempts to understand motion, leads him to deduce the laws of gravity. He invents calculus. And he also figures out his 3 laws of motion. And that's about it. I think we're going to stop there.